So the presentation has been divided into 3 sections. So background, personalized federated learning for heterogeneous behavior modeling, and finally, there is a project about how to use inter and inter-agent agreement to address behavioral competitive objectives. So we begin with what affective AI is. So affective AI is a computing that is grounded and associated with human emotions, and it involves recognition, generation, forecasting, and also estimation of affective states. So the question is, why do we even need to do affective AI or multimodal behavior modeling? So as we know, in today's world, human AI teaming is increasing, and affective aware human AI agents, they can allow more smooth collaboration in case of human AI collaboration. In addition to that, in case of human-computer interaction, any user interface that is aware of human affect states can provide better user experience than that of a naive human-computer interface. Additionally, affective AI, it has been used and also experimented mostly in the field of education, health, and also cybersecurity. So let's dive into some of the characteristics of affective AI. So when we look into emotional expression, it has multiple different intensity levels. For example, when you look into this image, it shows different intensity level of the happiness expression. So to your left, you can see more neutral or more close to neutral, but still happy expression of more serene facial expression. And to your center, you can see more content expression. And to your right, you can see more exaggerated or more elated, happy facial expression. So this shows that human expression, it can have multiple intensity levels. However, when you look into it, most of the natural expressions, they are much more subtle and they are much more short-lived as well. So what challenges does the subtlety of human behavioral expression arises? So based on the most of the literature and most of the corpora that we look into, they consist of actors and directors. So usually data collection, they hire actors and ask them to act certain emotions. However, those acted emotions are mostly exaggerated and they do not represent the actual natural expression. So most of the models that work on that kind of expression, they usually fail on realistic and naturally occurring expressions. So next, we will look into more of a perception now. So our usual assumption when you think of machine learning or other aspect is that concepts, they usually have a single and clear interpretation. So let's look into some examples. So here, the task is to classify cat versus dog. So when we look into it, we can clearly see the first one is dog and the second one is cat. So the second task is polarity classification. So as we can see, the first sentence is I'm beyond happy to have won the lottery. It more conveys positive polarity, whereas the second one, it more conveys negative polarity. So the question is, does the assumption of having a single clear interpretation, does it always hold? And the answer is, in case of behavioral modeling, there can be multiple different point of view and multiple different perspective. And there are the cases of genuine disagreement where all of them, they can be equally valid and hold all at once. So let's look at the example. So given this busy street, so the question is, who is the main character here? Yep. Okay. Some other.
The person drawn.
Okay. Yes. Yep.
I'm gonna go point of view and say the person that's taking the photo, like it's a point POV kind of like perspective, right, on the main character.
Yep. Yes. Okay. So in this case, so this shows a view of multiple different perspective or multiple different point of view. And in this case, all of them, they are equally valid. So let's look at the second case. So what is the dominant emotion, or like what do you observe here? Yep.
That's slightly two.
Yes.
Happiness and disappointment.
Yep. So in this case, what we see is two different opponent teams, and they are experiencing two different kind of emotions in multiple different levels. And so here to the blue, we can see they are more sad, frustrated, and to the right, they are more happy, excited. So it also shows like even though they are looking into the same thing, they are experiencing different thing based on their own biasness, they based on their own perseverance. Okay. So next. So now we looked into two different visual cases. Now let's dive into the language case. So here is an utterance. So what do you think the utterance convey? What kind of emotion does it convey? Yep, irritation. Okay. Any other? Okay. So here we go, even from, yep.
I'll just say to my wife, I'm concerned.
Uh, so this kind of statement, it shows that multiple different perspective or multiple different context or multiple different point of view, they give you different answers. And in this case, they are all equally valid answers. So next, let's look into how affect has been usually modeled in case of affective AI. So first, let's look into modeling of affect in language. So when we think of language or text-based, especially text-based language, we think of them as a means of conveying informative content. However, in addition to that, they can also convey affective semantics. Uh, and sometimes when there is only text, they can also be ambiguous. So to your right, we can see a table where we have the first sentence is only conveying a single emotion, whereas the second sentence is conveying multiple different emotions. And sometimes having context helps. So let's look into some of the cases. So here, given the context in the bold uh, text, we can see the text in the green, it more conveys more of a amusement. However, when there is, in case of other second one, having the context, it still might convey more than one affective states. So in case of affective AI, having context also helps, but in some cases it doesn't help. So it also depends upon how much context is there. So apart from text, when we have multimodality, they can also help. So in this case, we'll look into prosody as it conveys not just what people say, but how people say it. So let's hear the sentence, the given sample sentence in two different emotions.
You got to be kidding me.
Is that loud?
You got to be kidding me. You got to be kidding me.
So here, what we can hear is there is certain outburst of vocal outburst in the beginning, and then they suddenly decreases. So this is the case of anger. So let's look into the case of surprise.
You got to be kidding me. You got to be kidding me.
So here we heard the same statement in two different prosody or like with two different voice inflections. So the first case, it was of more of an anger, and the second one, it's more of a surprise. So in the first case, when there is anger, there is certain vocal outburst in the beginning, which slowly dies. So because of that, there is high pitch in the beginning and the pitch slowly dies. However, in case of surprise, the pitch somewhat remains high throughout the utterance. However, in this, it peaks in the case of kidding, which is the central element of surprise in case of this utterance. So now let's look into some of the resources that we use for the subtle multimodal affective behavior. So we mostly focus on three different data sets. The first one is Fuse, which we collected in our own lab. And the second one and the third one, IMOCAP and MSP Improve, they are collected by the team of Busso. So we consider this data set mostly because my research, it focuses on dyadic interaction, where there is interaction between two or more individuals and they are having some conversations. So when you look into scenarios, so most of the, as I said, previous data set, they consist of usually the active data. So even if you look into iMoCap and MSP Improve, so they have scripted as well as improvised data set, whereas Fuse, it more focuses on natural interactions. And looking into the annotation methods, so in case of Fuse, we use both annotation for self and also the annotation for partner. whereas in case of IMOCAP and MSP Improve, they focus on self and annotation by other multiple raters. So having looked into the variation in perception and variation in expression, what we know is, and also based on the literature, what we know is most of the previous approaches, they work on centralized approach, where they collect data set from all of the individuals and they train a centralized model. And having the centralized model, it often provides a generalization. However, it is always done at the expense of personalization, because when we generalize all of them, the individual performance, they are somewhat degraded. So for this, we explore personalized federated learning as a way of dealing with the heterogeneity within the individuals and for better personalization. So let's look into what federated learning is. So federated learning is a decentralized machine learning approach, and it trains multiple models across multiple devices and without sharing of information. So let's look into how it works. So here we can see server to our top and the clients in the bottom. So it more correlates with the client server model in case of network architecture. So the first, there is model initialization in the server, and the model is broadcasted to all of the clients. Second, the client models, they train the model with their own dataset. And then the third, the trained models, weights, they are updated to the server. And finally, the server, they perform the global model aggregation and update it. So at the end of each communication round, they also send the finally updated model to each of the clients as well. So here we can see two special things. So that is privacy preservation and data security. So this was one of the main reasons why federated learning was started in the beginning for the first point as well. So federated learning in itself, it mostly primarily focuses on having a better server model, and that is for better personalization. Better generalization. However, it somewhat ignores personalization. So there is a field of study within the federated learning that's known as personalized federated learning, that focuses more on the local client performance than that of server model. So my work now focuses now more on this approach of federated learning. So the whole point of using federated learning here is to formulate the personalized emotion recognition problem is more of a federated learning problems. And so where each individual client, federated learning client can be represented by actual human individuals and their data. So since we already discussed that there is a variation in emotion expression as well as variation in emotion perceptions, so this leads to heterogeneity. And then in the next slides, we'll discuss about what kind of heterogeneity can we observe. So heterogeneity exists in the behavioral modeling, especially in the case of human behavioral data. So for any individual, so given the features and the labels, we observe the top three expressions. And given the expression, we can observe four different kinds of heterogeneity within the behavioral modeling. The first one is feature skew. That is, since individual way of expression is always different to that of from one individual to another individual, it arises the case of covariate shift or feature distribution skew in between the individuals. Similarly, since the perception and also the expression is different, it also results in the difference in distribution of the levels, unless it's a case of highly simulated or highly controlled data collection in case of some labs data collection, where we might have somewhat similar or almost the same kind of level shift, but in most of the cases, we'll observe some level shift. And finally, there are concept shift and concept drift, where in case of concept shift, so similar features or similar expression, they can yield multiple different perception or multiple different effect levels. And conversely, so similar features or similar affect states also can be conveyed in multiple way by different individuals. So this leads to the concept shift in behavioral modeling. And finally, there can also be the data quantity skewness, where different individuals, they might have highly imbalanced number of instances for the modeling purpose. So next, let's move back to the dataset that we use specifically for this study. So since this study, it mostly focuses on dyadic interaction, where two individuals, they are interacting with each other. So the dataset that we use here are IMOCAP and MSP Improve. And from within the IMOCAP and MSP Improve, we mostly focus on improvisation and the natural interaction data as they like closely represent to the natural interaction as opposed to the acted scripted data. So for the feature extraction, we use pretend models. That is, we use Gecko model for getting the embedding of the utterance text, and we use wave to wake for the audio utterances. And finally, we also made a new modality just by night concatenation of the verbal text and the speech audio. So next, let's look into some of the results or some of the observation that we observe in case of more heterogeneity. So here, the result, it shows the utterance distribution per individual for IOMOCAP and MSP Improve. So here to the bottom, we can see the small boxes, they represent each session. So each consecutive pair, they represent each session within the IOMOCAP and MSP Improve. So for example, here the first pair, they belong to session 1. Second pair, they belong to session 2. So they are the pairs which are interacting with each other and which are exchanging utterances with each other. So based on so here we can see the utterance count within the same session, they are somewhat consistent than that of the other utterances. This shows somewhat behavioral synchrony in case of dyadic interaction. And in addition to that, when you look at the levels of the all of the within the same client and also different between label distribution between the same client and also within the different client based on the JS divergence, we also observed more similarity in between the labels between the same clients than that of the other clients. This shows emotional synchrony of the uh, uh, dyads in case of the dyadic interaction. So this results, it shows feature distribution skew using automobile systems. So here we can see heat maps. So it basically shows the heat map, automobile distance between the different clients feature space. So one of the things that we can observe here is that the individual heterogeneity is much more higher in case of speech than that of text, which is somewhat expected. And the combined, it somewhat lies in between. And the other thing that we can observe is a 2x2 lighter uh, table along diagonal, which shows that there is more similarity in case of feature in case of expression, which is represented by the feature distribution within the same session than that of other session. So this represents the behavioral synchrony. So now we observe two kinds of synchrony in case of the dyadic interaction. The first one is behavioral synchrony, and the second one is emotional synchrony. So based on the synchrony, to utilize and to capture the dyadic interaction, we introduce an additional aggregation layer, the middle one. And so, and based on this, we introduce a new personalized federated learning approach called Fed session, and it's a tiered, and which in addition to previous one, it adds a additional aggregation layer. So let's talk about them in details. So here, the bottom layer, it represents all the individual clients. And here we can see there are multiple different clients. And those clients, they belong to each session. And each session, they also can consist of one or more than one clients. And there is no overlap of clients in between the sessions. And for the model update of the clients, based on mammal-based approach, we update the session models using the we update the session models with respect to the loss function of the client models. It is communication round. And for the intermediate aggregation, the second one, it acts as a more of a bridge. So it acts as a client for the server model, global server model, and as a server for the client models. So here, in case of intermediate aggregation, we train multiple different session models, which is equal to the number of sessions. So basically, each session, they have one session model, and those session models, they are personalized for the group of local clients. For example, this session model is personalized for more of the session clients within the same session only. And they are updated by minimizing the corresponding loss of the corresponding clients, losses of these corresponding clients. So finally, there is a global model generalization, and it basically aggregates the session models. So, and for flexibility, we allow using any different kind of other previously existing personalized federated learning approach at the top layer, while we use only mammal-based approach for the clients. So the whole point here is using the global server model to increase the overall network performance and also for more better generalization to the new clients. So let's look into the experimental setup for this one. So for simplicity, we only use two-layered fully connected neural network, and we use early fusion, and phalanx are the training setup. And for baseline and comparisons, we compare our fade session approach with fade averaging and fade FOMO in the top layer against local training and other previously existing standard personalized faded learning approaches. So here we can see the performance of various different approaches for IO mocap and MSP improve and its multiple different modalities. So let's look into the results. So first, let's look into the performance of the prior existing approach, which is that of local training. So local training here simply means training the individual client with their own data, and there is no aggregation in the server. So it basically training the own each client trained with their own data and test it there with their own data. So we can see that previously standard faded averaging, fade FOMO, and for fade averaging, they perform significantly worse than that of local training. And only the faded averaging, it performs better than the local training only twice, and also by like small margin. So this basically means that there is even no point in doing faded learning. It's like even if we are doing faded learning, it's not doing anything, and it's better just doing local training. However, if you look at fade session approaches, it always performs better than that of the local training. And also like only once in case of fade FOMO, so the combined of the MSIO mocap, we can see it performs comparable result to that of fade FOMO, where fade FOMO it most of the time performs even worse than local training. So these results were also shown significantly, statistically significant by t-test. So we can see the results for here. And in addition to that, one thing that we observed was using early fusion gave better results than that of using a single individual modality. Okay, so next, let's go into the second project. So as we saw, like previously we discussed about the problem of generalization. Is generalization has been done mostly in case of behavioral modeling. And second, we moved into why we need to do personalization and a method for personalization. So the question here is like, are there cases when personalization is better, and or are there cases when it's better to generalize? So for that, we look into leveraging inter and intra-agent agreement in case of data perception to address the competing behavior of when to personalize and when to generalize. So let's look at a case of variation in perception. So here you can see to your middle is our expression, and to your left you can see human agents, two human agents, and the two human agents, they look at the expression and they perceive what the expression is. So here the first agent thinks the person looks happy, and the second agent thinks the person looks more of a surprised. So it shows a case of disagreement, or we can say it's a more of a inter-agent agreement. Next, the same individual who annotated the expression is surprised previously might at a different time annotate the person looks happy. So it shows even the person at different point of time can change their perspective. So next, let's look into how we can calculate or we can get inter and intra agreement in case of corpora, or like when we collect it on our own. So for this, let us consider our classification task, where we have a classification task of classifying multiple different samples into class A or class B. And let's us consider there are three different human annotators or human agents. So for any sample N, so each of the agents at a time would give their annotations. For example, here, let's say it's A, B, and B. But at different point of time, the same agents might annotate it as A again. The second annotator might annotate it as B again. However, the third agent, it sometimes might change their annotation. So here, it might mean two different things. The first thing is the annotation behavior of the first and the second agent is more consistent or more stable, and that of the third one is unstable. or in some cases, there is an update in information or knowledge in the third agent that is changing its annotation. So in this example, we'll simulate this behavior to get the values to get inter and intra agent agreement and see what kind of case would they be useful in. So for this, utilizing the inter and inter agent agreement, we propose a taxonomy for those agents. So here, when I say agents, it could mean they are all humans, or they could be human all AI agents, or in some case, it could be human AI agents in case of human AI collaboration. So given the inter-agent agreement and intra-agent agreement, there can be cases when there is high intra-agreement or low intra. So for the case of ease, let's say the case of high intra is more stable and the case of low intra is less stable. And the case of high inter is more reliable and the case of low inter is less reliable. So in the case of high intra and high inter, which is mostly the case in most of the machine learning case, is more suitable for to generalize. So however, in cases when there is high intra, that is the same agents, they agree with themselves at different point of time. However, there is low inter, that is they do not agree with each other at multiple different point of time. And this basically means it's better to personalize, citing there is uh, more of a subjectivity within the agent itself. So for this kind of case, we propose to more personalize. And then there can be case of low intra and high inter. So this is one of the most peculiar case, as you might think that different agents, they agree with each other at different point of time, but they do not agree with themselves at different point of time. So this is one of the most peculiar case. So if you look at it, most of the literature, they have cited them as more of a noise. However, what we think of them is, in some cases, there can be an example of knowledge update. For example, you are believing something, and then all of you learn certain different things, so that now all of you are changing your perspective. So in that case, it's more of a case of concept shift. So for this, concept shift approaches should be used, or it has to be realized whether there is noise or not. And finally, there is a case of low intra and low inter. So it's mostly the noisy case. And in this kind of task, the whole task has to be redesigned. So let's look into how we simulated the annotation behavior by the human individuals. And the thing is, for this, we used the Go emotion dataset, and it consists of multiple different comments with their individual annotations. For example, we use only the comments that had at least 3 annotators. So for example, the first annotator would have C1, C2, C3. And similarly, from this, what we can get is majority consensus. So majority consensus is basically we take, okay. So let's look into this annotation setup for this study. So for this study, we used Go emotion dataset, and as they have labels. So one thing that you can see here is like we have asterisks after like 1, 2, and 3. And the thing is like, in case of Go emotions, there were like only very few common annotators who annotate the same comments. So for that purpose, we couldn't use just the same annotator in the Go emotions. So for that purpose, we had to simulate the human annotation process. So for the simulation, we used 3 different LLMs. We used FLAN, T5 large, and then we used Mistral and the Llama to simulate the human annotation process. So for this one, we divided the whole data set into the fine-tuning data set and the test set. So for the fine-tuning, we used we fine-tuned the behavior of the LLMs to simulate the human behavior, and we tested everything. We tested the annotation behavior in the test set or the held out set. So let's look in. We trained the whole LLMs in 2 different ways. The first one is more of annotator wise. So here we trained each of the LLM using individual annotation from the Go emotion dataset. And in addition to that, we also trained them using single consensus, where all of the LLMs were trained on the majority consensus. So after they have been like fully fine-tuned, what we did was like we also tested, we also used them for zero-shot annotation on multiple different the held out data set. So based on that, we observed these results. So the first question here is the ecological validity. So when we think of LLMs, we think of them like fancy and it could be easily used. But does using the human LLM to replicate the human consensus, does it make sense? So for this, we calculated Cohen's kappa and for both soft and hard comparisons. And here we have the results for multiple different LLM settings. So the FLAN and the FLAN star. So the FLAN is just the base FLAN model, and they were used for annotation using zero shot, and the flying star is the fine-tuned one, and they were used for zero shot. So based on the results, what we can see is there is moderate to substantial agreement based on Landis and Coates' interpretation of the Cohen's kappa, and this supports the use of LLM to replicate the human consensus and also use of the LLM for the remaining of the experiment. And the second thing that we observed was that the annotator-wise fine-tuning introduced more ambiguity as it was expected, since they were trained on individual human annotation rather than a majority consensus. So here we see the results of the inter and inter-agent agreement. So across the diagonal, we can see the intra-agent agreement. So this is the agreement between the same individual. So here is the agreement between the plan model with itself at different point of time. So along diagonal, we can see all of them, they have substantial agreement with themselves. So this basically means even if they are not that good in case of like annotating or do not have is high human consensus level, but they are stable in themselves. And when you look into inter-agent agreement, only in case of the fine-tuned one, only the fine-tuned models, they have high inter-agent agreement within themselves, and they have quite low with that of the other non-fine-tuned ones. So the result here, so here it shows a two-dimensional Cartesian space. So where we have inter-agent agreement along the x-axis and intra-agent agreement along the y-axis. So this is the same result as the previous one where we only plot it in this Cartesian. So one thing that we can see here is all of the intra-agent agreement, they are quite high. So in our case, we can only represent the case of high intra-agent agreement. However, we can observe the case of high and low inter-agent agreement based on and the Landis and Coates interpretation. So here, the vertical line, it divides the case of having low inter and high inter. So let's look into two examples. So first is the case of fine-tuned Mistral and fine-tuned Flan. So here we can see they lie in the region of high inter and high intra. And for this kind of example, we propose on more of a generalization-based approaches. And the next one is fine-tuned Flan and base model or unfine-tuned Mistral. So in this case, we can see it's a case of low inter and high intra agreement. And for this kind of method, we propose personalization based on the taxonomy. So here is the result for the multiple different agent comparisons. So here we can see each row, they represents two different agents and their performances. So the first column is personalization. It shows local individual training. And then there is generalization, that's centralized training. And then there is delta, that's performance change. So let's look into the two previous examples. So the first one is the case of Mistral and fine-tuned Flan. So one thing that we observe here is there is quite high personalization performance, and there's sharp decrement in case of the delta, that is the performance difference between personalization and generalization. However, if you look at the case of fine-tuned Mistral and fine-tuned Flan, what we observe here is we can see there is still high personalization. However, there is increment in the generalization as well, and there is only small decrement in case of the delta. So these results, these outcomes, it somewhat aligns with the taxonomy and also suggests the use of the taxonomy as a tool to decide on when to personalize and when to generalize. So these results were also further validated by the uh, Pearson's correlation assessment. So here we can see that the inter-agent agreement, they are highly correlated, strongly correlated, positively correlated with that of generalization, and they are negatively correlated with that of the delta. So from the analysis of the delta value, what we can analyze is through the strong negative correlation, there is indirect or negative correlation with the personalization as well. And in our case, since we have the exact same feature space and different label space, then because of that, the generalization, it cannot reach as much as that of personalization. However, if we have extreme variation in case of diversity, in case of the feature space, we'll observe the same kind of better generalization than that of personalization. So finally, as a conclusion, so we draw three different kind of conclusion from this study. The first one is there is variation in human behavior expression. However, there is also multiple different valid perception. And knowing this, we have decided on when to personalize and when to generalize. And the second one is the use of the fate session approach and the intermediate session layer. It helps for better dyadic personalization. And finally, the use of intra and inter-agent agreement. It can be used as a tool to guide on when to personalize and when to generalize. So the next step would be to increase the exploration of multimodality and also make use of the fused data corpus that we collected in our lab and analyze the inter and inter-agent agreement in case of multimodal expression. And finally, the other next step would be to extend experimentation with other personalized fate learning approaches, leveraging to quantify emotional synchrony in case of dialogues and to leverage it to improve further personalization. And finally, the main task would be moving towards more human AI collaborative scenarios. So I'd like to thank all of my lab members in my lab, especially Dr. Cecilia Am, who is my supervisor, Michael, and Cedric especially for recording all of the audios, and Sophia and all of my lab mates. And I would also like to thank NSF for fundings